So last time we talked about conditional probability and independence. And I want to jump straight into a question, which is what's the definition, according to how we presented it last time, of the term independent? And specifically, we're thinking about events here. So two events, A and B, are said to be independent if okay, excellent. So several good answers here and running along different lines as well. So this is the sort of conceptual idea. Knowing something about one of the events does not tell you any information about the other event. In other words, if you update your probability measure in accordance with the information that one of the events occurred, then your new probability measure gives the same probability to the other event as it did before. So it doesn't change. And here's a mathematical expression of that exact idea. So this is the formula for the conditional probability of A given B. And this is the expression on the right-hand side here that needs to be the same as the probability of A if you're going to say that the two events are independent. And you can unravel that a little bit and rewrite it as the probability of A intersect B is equal to probability of A times probability of B. So a couple of folks wrote answers like that. This notation might look wrong if you haven't seen it before, but this is a thing that people do. If you juxtapose events in notation, that normally doesn't have a meaning, but some textbooks will define it to mean intersection. And it's kind of nice actually, because if you think of events as indicator random variables, then multiplying those random variables corresponds to taking the intersection. So I rather like this notation, but in any case, lots of correct answers here. And the bottom line is that two events, A and B, are said to be independent if the product of their probabilities is equal to the probability of their intersection. And incidentally, this requires that A and B be defined on the same probability space that has a probability measure associated with it. So this is not something that you can see at the set level. There has to be a probability measure there because you're taking probabilities on both sides of this equation. Also, they have to be defined on a common probability space in order for it to make sense to take their intersection. So we have seen examples of things that don't require things being defined on the same probability space in order to work. For example, two random variables can be said to have the same marginal distribution, even if they're defined on different probability spaces, because ultimately we're comparing two different probability measures on the real number line. And we can do that whether or not they came from the same probability space. So it's sometimes helpful to bear in mind whether particular properties pertain to the probability space that two things need to both be defined on, or whether they're somehow emergent properties that we can forget the probability space in order to make comparisons. Okay, so here's a drawing exercise. Here's an example of a probability space with probability mass function indicated by the labels. So this is a 9-element probability space, and the masses are as you see them here. So we talked about this last time. The goal here is to select two independent events in this probability space. So you're going to want to indicate a particular event just by enclosing its elements with loops. That's usually the easiest way to do it. Okay, so a few folks are still sketching. I want to give a wrong answer first so we can think about why it's not correct. And then we'll talk about a correct answer. So what if I choose, let's say, those two elements and maybe these two elements? So if we choose disjoint events, how do we know that they're not independent? Okay, great. So we have here a math answer and a sort of verbal answer. These are both good. So if you know one event has occurred, then you know the other one has not occurred. So if two events are disjoint, then that's exactly what it means. They can't both happen at the same time. So if you know one happens, you know the other didn't. So it's not the case that learning information about the occurrence of one event tells you nothing about the other one. In fact, it tells you everything about the other one, namely that it didn't occur. Another way to see it is to use the intersection definition. The probability that A and B both occur is 0, just by definition of disjointness. Actually, that's slightly imprecise. The intersection is empty by definition of disjointness, and then the probability of the empty set is 0. So in any case, we definitely can't be selecting disjoint sets here. And really the key idea is that the construction that we did for this probability measure, the point was to make it so that the random variable, which says what's the horizontal component of any given element here, and the random variable, which says what's the vertical component, so we might call those X and Y, those random variables are going to be independent. So if we ask something like, what's the probability that Y is equal to 1? Or what's the probability that, what's the probability that X is greater than or equal to 1? So this event pertains only to Y, and then this other event, the sort of larger one, pertains only to X. And the point of this construction was to obtain X and Y as independent random variables. And that means that these two events are going to be independent. And you can work it out. The probability of this event is 1/2. The probability of this event is 3/4. And the probability that both happen is going to be 1/2 times 3/4. So this is an example of a pair of independent events. So I'll insert that and send it. And here's the sort of version of it that I prepared, just explaining what I just said. So this blue set here is saying, is X greater than or equal to 1? The orange set is saying, is Y equal to 1? And those are independent. So where did this probability measure come from? I want to put this picture up again because I think it's really helpful. We obtained this particular probability measure not by some exploratory means, but through a construction that we can always repeat to obtain independent random variables. So we had a random variable X with this quarter, half, quarter mass that we were interested in. And we happen to want the same distribution for the Y coordinate as well. And then we were like, okay, well, we've got these masses here and these masses here. We need to sort of interleave them in some way to create a probability measure that has the right properties in both dimensions and exhibits independence for these two random variables. And the way we did it is that we just multiplied across vertical and horizontal lines through all of the original masses and wrote down the products in those locations. So everything gets smaller here. So you have, a 1 unit of probability mass along the horizontal line. You still have to have 1 unit in total once you spread it out across the plane. And so things have to get smaller. And they do that by multiplying other probabilities. So like this 1/2 is going to hit this 1/2 and produce a 4th here. This 1/2 is going to hit this 1/2 and produce an 8th here, and so on. So this is how we got that product measure. And it might seem a little bit surprising that this consistently produces independent random variables, but it's actually just a distributive property that gives us the independence property here. So I want to spell that out so that it's really clear that there's not any real magic going on behind the scenes here. It's really just a distributive property. So what I want to do is write the probability masses as A, B, and C. Move this up a little bit to make it clearer. So A, B, and C along the horizontal direction, and D, E, and F along the vertical direction. And I put the variables there in place of the numbers just because it's easier to see how to do algebra with letters instead of numbers. So if you multiply this through, you just get the same thing as before, CF up here, BE here, CE here. Everything is just a product of whatever the X mass was along that vertical direction and what the Y mass was in the horizontal direction from that point. It's like AE, BE, CE, that's because E was right here. So if we ask for something like what we just illustrated in the previous exercise, the probability that X1 is greater than or equal to 1 and X2 is equal to 1. So, okay, I guess I switched names a little bit. Instead of X and Y, I'm calling them X1 and X2. Either way, they mean the horizontal and vertical random variables here. So the random variable which takes each point and produces its horizontal component, and the one which produces its vertical component. In any case, what we're asking here is this horizontal random variable either 1 or 2, and is this vertical variable equal to 1? So this is the event. That's the intersection of the two events that we sketched. These are the only two that satisfy that condition. And the probability is equal to BE plus CE. So we just add the probability masses for those 2 points. But of course, if you just reverse distribute that, you can get that as E times B plus C. So in the picture, you can see how the sum of the masses here just factors as however much mass was in this set along the vertical axis at the beginning and however much mass was in that set along the horizontal axis, just because, again, distributive property of multiplication over addition, that's going to give you that property for any sets that you choose in this way. So we could extend this horizontal rectangle to include this point. You get the same idea. Really, any of these rectangles that you can imagine constructing are going to have the same property for exactly the same reason. These two messages saying what I just said, B plus C times E is going to give you the probability mass of the intersection, and that factors as, you know, the probability that x1 is in 1, 2 here times the probability E that x2 is equal to 1. All right, and there's nothing special about that set. That's going to be true no matter how we choose these sets A and B. Okay, so maybe I'll pause to ask for general questions. So any questions so far about the product measure construction? Okay, so let's move on. If you have a question, feel free to still type it and I'll pick it up when it comes in. Okay, so we're going to extend this. Like typically in the real world, you don't want to talk about just 2 random variables being independent. You often want lots more than that. So for example, if you playing Yahtzee and you're rolling 5 dice, like that's 5 random variables that should be independent because they correspond to different dice that are not really somehow seeing each other or affecting each other's outcomes. So the idea of just having this kind of rectangle and multiplying sort of vertically and horizontally to get this product measure in the plane, it's fine as far as it goes, but you do want to do more than that. But the thing is, we don't really have to do anything different. We can just throw an extra set into that Cartesian product. So instead of multiplying, along the x-axis times along the y-axis, we just throw in a third axis. And if we have 4, then same idea. We can't really visualize it the same way anymore, but still mathematically, it's just fine. We just construct all of the tuples that you can make to selecting one element from each of the sets, just a normal Cartesian product in the set theoretic sense, and then we just multiply probability masses. So I want to ask a question to kind of to highlight that. So suppose we're going to roll 3 dice, and suppose that each one of the dice is weighted in such a way that the face that has 6 pips on it has a 1/2 probability of turning up, and each of the other 5 sides is equally likely with a 1/10 probability. So the set of possible outcomes, just like for any triple of dice, is going to be the set 1 to 6 cubed. So that's the 3-fold Cartesian product of the set of integers from 1 to 6, or in other words, the set of all triples of possible die roll results. In that probability space, what probability mass should we associate with the outcome where we get 6s every time, 6 on each of the 3 dice? Nice, okay. So folks are getting this one right. So you want to put a probability mass of 1/8 on that particular outcome. And there's nothing that special about this particular outcome. Actually, before I proceed, I kind of want to hear from someone because I don't think we've heard from anyone yet. So Radhika, you have a check mark and you have a correct answer out here. Would you like to explain how you came by this answer? Right, so that's it. So we're, in some sense, you can think of this as just an ordinary probability exercise where you're asked to sort of recall that independence means multiply. Another way of thinking about this is to go back up to this picture and remember that when we made this construction, we're multiplying along horizontal and vertical lines in pairs. And so we're doing the same thing really, but just in 3 dimensions. In this dice example, you're going to have a 1/2 associated with one outcome, multiplying a 1/2 with another, and it's still a third factor of 1/2, producing a factor of 1/8 sitting at that sort of one locus in this probability space. You can imagine it as a cube with, a 6 by 6 by 6 cube of dots, and one of those dots is going to have a probability mass of 1/8 on it. And we're going to give probability masses to all the other dots too. So for example, 1, 1, 6 would get a mass of 1/200th, whereas 6, 6, 6 gets a mass of 1/8. So this is a way of constructing our probability measure. And then once we have that probability measure constructed, we're going to know that all the events pertaining to separate dice are independent from each other. So then once we have this construction, we can say more general things like the probability of getting a 3 or less on the first die and the probability of getting 6 on the second die, you can talk about the probabilities of those two events and multiply them, or you can talk about the probability of the intersection of those events, and you're going to get the same result either way. And that follows from the product measure construction. So in some sense, this exercise kind of gives us a different perspective on this diagram, which is that if you want it to be the case that independence means multiply, that has to be true at the level of individual outcomes. So events consisting of only one outcome. And that forces what the probability masses have to be at each of these particular like single outcomes. And then the point is that construction actually gives you independence for all the other events just by distributive property. In any case, this is what's going on here. So in your mind, if you're needing to envision a probability measure associated with some random experiment that has lots of independent random variables in it, you should be thinking of a high dimensional cube, kind of like this particular experiment only has 3 independent random variables that we're trying to account for here. And already we're looking at a cube, a 6 by 6 by 6 cube. You're going to have a very high dimensional space if you have lots and lots of independent random variables that you're trying to model. So I want to illustrate a kind of counterintuitive fact about joint independence. So independence of several random variables. This is a stronger condition than just knowing that they're independent in pairs. So you might think something like, okay, well, A has nothing to do with B, B has nothing to do with C, A has nothing to do with C. Like, what more could you want? They're all independent. None of them has to do with anything else. But this is not actually the case. You need a stronger condition in order to say that random variables are jointly independent. In other words, their joint distribution is the product measure of their individual marginal distributions. And I really like this particular example for conveying this idea, because I think once you wrap your mind around it, it becomes fairly easy to remember compared to some other potential ideas. So here's the idea. We've got a 4-element probability space omega, and it consists of all the triples of binary values, so zeros or ones, where the sum is even. So that could be all zeros, or you could have 2 ones in the 3 possible places you can put them, and then that's it. So fairly simple, just all the triples of binary values where the sum is even. And the thing is, if you focus on any one component for defining an event, so let's say A is the event that the first entry is 1. So A consists of these 2 elements of the probability space. And B is the event that the second entry is 1. So that consists of this one together with this one, and so on. Similarly for C, then when you do that, you're going to get independence of any pair of these random variables. So if you just ask, okay, what's the probability of A, or what's the probability of B, what's the probability of A and B, those first 2 values are going to multiply to give the third one. So for example, probability of A is a half, because as we said, it has 2 elements in it. Probability of B is a half, because as we said, it has 2 elements in it. And that we're supposed to be considering the uniform measure on this probability space, or on this set omega. And the probability of the intersection, well, that's only this event. Sorry, that's only this outcome. So that event has probability a quarter, and a quarter is a half times a half. So that checks out. And by symmetry, the same is true of the other ones. However, what happens if we consider the probability of A and B and C? So I'll type that in as its own question. So what is the probability of A and B and C? So the probability of the 3-fold intersection is 0, because no outcome has all of its entries equal to, all 3 of its entries equal to 1. That's exactly right. So 1, 1, 1 is omitted from this set. So that's it. Another way to think about this is, so A and B, A and C, and B and C are all independent pairwise. But if I tell you A and B, then you know C for sure. So if I tell you what the first 2 values are in the triple, then the third value is forced by the fact that the sum is even. So you're able to learn nothing from one set, any one set, but learn everything from more than one set at once. So if you know A, you know nothing about C. If you know B, you know nothing about C. But if you know A and B, now you know everything about C. So it's kind of depending on how you're modeling these sorts of things mentally, it's potentially quite surprising that this would be possible. Like if you think of it as like sort of knowledge accumulation as sort of trackable by a real number, A tells you nothing, B tells you nothing, nothing plus nothing better be nothing. But it's just showing you that the relationships here are more complex than simply adding information, right? Joint knowledge is fundamentally different from individual separate knowledge of events. So I want to pick up a question that came in earlier that I think it's worth expanding on, because this is a very easy thing to get confused about. So what is the deal with this product measure business? That's the question. So it sort of seems like we're getting this product measure construction from reasoning about what independence should look like, but yet we're calling it a construction. Like, isn't it something that emerges from the random experiment? I think that's a fair point. The response that I gave here, which I'll also share, is that we have a random experiment. The idea is like you're rolling a die multiple times or something, or flipping a bunch of coins, and you want to model that random experiment in some way. You need to construct a probability space that has the right properties to describe that experiment in an accurate way. And the product measure construction is what's going to do that for us. So it's not quite like some other situations where you're able to sort of start with the probability measure and then work out properties of it. We kind of tend to end up running that in reverse. We want the properties, we want these independence features for our probability space, and we use the product measure to construct them. You could imagine doing it other ways, but this is just how I try to develop it, to try to make it kind of all hang together in a way that makes sense. Okay, so just to put a bow on that exercise, the bottom line is that the probability of the intersection of events is 0, whereas if you just try to multiply probabilities, you get 1/8. And the notion of joint independence is that you can take any collection of these events and multiply their probabilities and also find the probability of their intersection, and you should get the same value. So that's the notion of independence for more than 2 events, and it fails here for these. So the events are not jointly independent. They're only independent in pairs. Okay, so let's move on to the next section of the course, which is going to be on expectations. So I'm going to be following the data gymnasia fairly closely here. So the idea of expectation is to produce a one number distillation of a probability measure. So for example, if you have a bunch of people and you want to select the height of one of those people uniformly at random, that's a random variable, but its distribution is really complicated. You basically have to make a table of all of the heights of all the people in the population and then communicate that table, maybe in a CSV file or something. It's going to take up some space if the population is big. And it might be a good idea to communicate just one simple piece of information to give people kind of a ballpark. Like you're talking to aliens and they're like, how tall is your species? You don't want to give them a huge file. You just want to give them a number. And expectation is a way of kind of distilling that large amount of information down to sort of a summary value. So in any case, hopefully people have mostly selected the answer here. This is a softball. This comes from back when everything was on Mathagon. It's very common to have these sort of like really basic check for understanding questions just to kind of keep your head in the game. And I left some of those in there. So anyway, if you want to calculate a uniform average, then you total up and divide by the number of items. That's a kind of, everybody's seen that a bunch of times. So yeah, so what's the term here if we're wanting the average to take place in a non-uniform way? So you want to somehow prioritize certain elements over other ones, then what is that called? Yes, this is a weighted average. There's going to be a homework question to ask you to think more about weighted averages. So I'm going to leave that one there for now. Here's another way of thinking about averages that I really like. It's a sort of physics interpretation of averaging, where you think like, okay, what if I had these 5 numbers sitting at these 5 locations on the number line, and I supported the number line at this point, this orange point here, what would happen? Well, this part of the number line would go down and this part over here would go up. Just think about balancing something, a kitchen spoon on your hand. If there's more torque on one side than the other, it's going to twist in that direction. So if you want it to balance, you have to move it to a location where the net torque is 0, or I'll probably only be able to get close here, not perfect, but whatever. So that's going to be the mean, because the torque going in this direction and the torque going in this direction balance each other out. And just by way of reminder, torque from physics is the amount of mass times the distance to the fulcrum. So the orange point is playing the role of the fulcrum here, and the further away you go, the more torque there's going to be. It's the reason if you're opening a door, you push on the end opposite to where the hinge is. You're going to apply the same amount of force, but it's going to have more effect rotating the door because you have a longer lever arm. You have your distance to the fulcrum greater than if you push near the hinge. And you can see that if you drag one point here. If I move it far away, it's going to have a lot of torque. If I move it close, it's going to have much less torque. In any case, that's kind of a couple ways of thinking about means if you haven't thought about it in those terms before. But what we're going to do here is focus on computing these kinds of weighted averages for random variables, or equivalently for distributions of random variables. And the definition we're going to take is just that we average the values that the random variable can take on, and we use weights, which are the probabilities. So it makes sense if you have a random variable that's like extremely unlikely to be 5, but it could be 5. That should carry very little weight. It should count, but it should carry very little weight because it's very unlikely to happen. So it's a really simple idea. You just take all the values that your random variable can take on, you weight each one of them by the probability that that random variable takes that value on. And that probability weighted average is called the expectation. So in math notation, it looks like this: that expectation of random variable x is all of the x omega values, all of the values of the form x of omega, each one multiplied by the probability mass of that particular omega. And then we just total that up over all of the probability space, all the elements of omega. So for example, if we're talking about our favorite random variable, the number of heads in 2 fair coin flips, the expected value is going to be 1/4 times 2, because there's a probability of 1/4 that the random variable is equal to 2. Plus 1/4 times 1, plus 1/4 times 1, plus 1/4 times 0. So this is the 2 heads outcome. This is the head tail outcome. This is the tail head outcome. And this is the 2 tail outcome. And it works out to 1. For each omega, we look at what x is, and that gets a discount based on how unlikely that particular outcome is to occur. We total all those things up. That's the expectation. And there are a couple of common ways of interpreting expected value. Go ahead and pop open your Python cell right here and just type in any expression at all and start it running, just so that your binder session will start up. So you can think of the expectation of a random variable as the value of a random game, where the payout is going to be equal to this random variable. So for example, according to this interpretation, if you're someone who gambles and you're rational, you would be willing to pay anything less than $1 to play this game that we just described, where you flip 2 coins and you get $1 for each head. And for more than $1, you should not be willing to play the game, because then it's favorable for the person taking the other side of that bet, and $1 is the break-even point. So another way of thinking about expected value, which dovetails with this first one, is that of a long-run average. So if you play that game a very large number of times, then typically your payout, almost always your payout, is going to be very close to $1. And the reason these 2 interpretations go hand in hand is that the reason that you're understood to be rational for taking positive expectation bets is that if you do that consistently over time, then under some conditions on the distribution of bets that you're taking, you're extremely likely to gain money in the long run. So it's very, very unlikely that you're consistently playing positive expectation games and you nevertheless end up losing a bunch of money. The exception would be if you're playing one really, really huge positive expectation game that nevertheless gives you a high probability of losing a lot, and then a bunch of small games, right? It doesn't really work out. But if your games are sort of similar in size and you play a lot of them, then the long run average is going to end up working in your favor, and you're going to make money in the long run. So that's why we say, you're rational to play positive expectation games. In any case, let's hope that this is done. It is, thank goodness. let's see how this second interpretation works out in practice. So what we're going to do is call randint of 0, 2 plus randint of 0, 2. This is going to simulate flipping 2 fair coins and summing the number of heads in each one. And we're going to do that 1,000,000 times. So this underscore is a variable name that you choose in Python when you're not actually going to use the variable name, which we aren't here since we're just using this expression which generates a random number. And then what we're going to do is sum that and then divide by 1,000,000. And that's going to give us the average number of heads that we got when we, or sorry, the average payout that we got when we played this game 1,000,000 times. So you can click run a few times here. That was quite slow. That's unfortunate. This, incidentally, is one of the reasons that in Data 1010 we use Julia. We do a ton of little experiments like this, and it's blazing fast. And here, obviously, you can see it's quite slow. Anyway, choose what you think is the most appropriate answer here. It's possible I need to revisit this question because it seems like it's maybe a little bit in between two of these answers. Anyway, I guess we'll see what people say. Yeah, so folks are saying around 0.001. Whatever. The point is, it's going to be quite close. And if you increase this number, if you go out, 10 times farther, it's going to be really slow, like really, really slow. Honestly, it might even break your binder server where this is running. This is Python for you. By the way, if someone else comes along and criticizes this, they're going to say, well, you should do all of this in NumPy. And it's slow because you're doing things in Python instead of NumPy. But it's kind of nice to use the language constructs, like list comprehensions are nice, and if you use NumPy, you can't do that. So yes, there is a trade-off where you can make this a little bit uglier and get it done faster, but it is a trade-off. And in Julia, you just write it in almost exactly like this, just slight modifications for the differences between the two languages, and then it's basically instant. Anyway, I guess we're not gonna get to see that finish executing. Oh, there it is. So yeah, so you see, you actually can't really tell. You have to run it several times to tell for sure, but it is getting that much closer to 1. It's only slightly closer if you go out by an extra factor of 10. Anyway, we'll talk a lot about this. This is an important idea. How quickly do running averages converge to their limiting value? And the most basic form of this result is a theorem in probability called the law of large numbers. But before we get to that, this interpretation, this sort of long run averages interpretation of expectation, gives us a useful tool for investigating the expected value of a particular random variable. Namely, we can sample from it a bunch of times and just take an average, and that's going to be an estimate of the expected value of that random variable. And this method of simulation is really important. In fact, in Bayesian statistics, there are going to be lots of problems where this is really your only tool available for estimating expected values in situations where it's far too complex to do it analytically. And it's called Monte Carlo approximation or Monte Carlo simulation. So let's see how we can do that in a situation where it's maybe a little bit, it's not terribly complicated, but maybe a little bit complicated to do this analytically. And we just want to sort of take the cheap way out and estimate this probability in a Monte Carlo fashion. So this is often going to be the case. You'll have a problem that's like fairly difficult, or maybe in this case, just a little bit difficult to work out analytically, but you can always do Monte Carlo easily as long as you can simulate the random variables in question. So let's say that you're going to roll 2 dice and take the quotient. So you'll distinguish them in some way so that you know which one's the first die and which one's the second die. You roll them both, you divide the first by the second, and that's the result. That's your random variable. And you want to compute the expectation of that random variable. So you can do that in a Monte Carlo fashion by sort of modestly modifying the code up here. So I'll give folks a chance to do that, and we'll see what we can come up with. So you have one answer in. Several folks are also working on their answers and doing a nice job. Some folks have different approaches. So if you finish up, feel free to go ahead and send it in. I'm just going to work through it here so that everybody's kind of on the same page. So let's just kind of start inside out and think about how to roll a die. So just one die roll. So you might think, okay, randint of 6, that seems reasonable. There's 6 faces on a die, but the problem is that gives you 0 and it never gives you 6. And so it's just shifted down 1. So you can either do +1 plus randint of 6, but that's a little, I don't like that so much because you're able to describe exactly the range that you want here rather than having to do an extra arithmetic operation at the end. So randint of 1 comma 7, that includes 1, it excludes 7. So this is the right idea. So we can do this whole experiment by doing randint of 1 comma 7 divided by randint of 1 comma 7. This is an important thing to know about random number generators in programming languages. When you call the randint function twice, or any random number generating function twice, unless you're doing something weird like resetting the seed in between calls, those are going to be separate calls that give different values. So I'll put a comma here to illustrate that. The idea is that these are going to be independent of each other. So I've seen a 5-1, a 1-5, a 3-5, a 3-2, and so on. So we can divide these, and this samples from the random variable that we're actually interested in. So it happened to be 1 1/4 there. I guess it was 5 and 4, 2, 1.3, 1.5, whatever. So we want to do this a bunch of times. We can do for underscore in range of 10 to the 6 or whatever, and wrap that in brackets. That's a list comprehension. That's going to give us a whole bunch of runs of this experiment. And what I can do is sum those. So I can replace the brackets with parentheses and put sum in front. And what that will do that's kind of nice is it doesn't store all the information. It's more memory efficient because it's just going to keep a running sum. And then what I can do is divide that by 1,000,000. And we get 1.427 something or other. So this is a suggestion that the mean is probably fairly close to this number. And actually we can work out exactly what it is. So, when I was saying in this case, it's a little messy to do this directly. It's not when you're programming, because you can just explicitly add up all of the relevant values. So I'll show you the solution I had prepared, which has that in it. So this is the same thing we just looked at. We can work out the actual mean by just computing sum of x over y for x and y ranging over all of the relevant values here. So for x in range 1 to 7, for y in range 1 to 7, compute x over y, total those up and divide by how many there are, which is 36. And we get 343 over 240, which is 1.429 some stuff. And that was like pretty close to what we got when we did this experiment. Couple digits of accuracy. Yeah, so any questions about that Python code? I really want to make sure folks have an opportunity to understand what we're doing whenever we're doing Python stuff, because I think that it's very easy if you're a little behind to start thinking about your Python programming in syntactic terms, imagining that you can sort of program by just kind of thinking of the next thing to type from beginning to end until you have something good. And it really doesn't work that way. The syntax that you actually see when someone writes some Python code is emergent from a semantic understanding of what they're trying to do and how the language works. So it's really important, if you see some unfamiliar syntax or you don't know how a certain function works, you want to make your units of knowledge as small as possible. You want to focus in on particular things. So for example, here you don't want to think of this whole expression as computing a quotient. You want to think of this part of the expression computing a die roll, this part computing a separate independent die roll, and finally the division just being a division of two numbers. Right? You want your comprehension of the code that you're interpreting to be as modular and atomic as possible. Drill down and understand each individual component, and then think about how they compose back to create a whole. If you're trying to comprehend the whole thing at once, then your knowledge is going to be too disjointed, and there's just way too much surface area to try to learn. You really have to make your knowledge composable for it to be useful. So anyway, it seems like no questions came in. Maybe that's clear enough. Okay, cool. Well, that brings us to 10 o'clock. So we'll pick up from there next time.